All right, everyone, welcome to lesson 17 and 18. Today we're going to be talking about different compounding intervals. We're going to talk about compound interest. So, what is compound interest? Compound interest is, before we get into that, let's talk about, right, we're going to this is exactly the definition, right? What happens when we repeatedly apply the same percent increase at different intervals of time? And so compound interest is interest calculated on the principal, which is my initial amount. Sometimes I'm going to always use initial amount, but sometimes out there you'll hear the word principal and interest accumulated over the previous period. And so we'll talk about what that represents in a couple minutes. So earlier you learned about a bank account that has an initial amount of $1,000 and earns 1% monthly interest. Watch your unit of time here. Each month the interest is added to the account and no other deposits or withdrawals are made. To calculate the account balance in dollars after 3 years, Elena wrote 1,000 times 1.1 to the power of 36. Tyler wrote 1,000 times 1.01 to the power of 12 to the power of 3. And so why do Elena's expression and Tyler's expression both represent the same balance correctly? And Kieran also gives the account balance in a different representation. We'll talk about what all of those represent. And so why do they both represent the same expression? Is because of exponent rules. And one of the exponent rules that we haven't talked about yet is the idea that if I take some a, the same base, power of 2, in this case it's 1.01, to the power of 12, to the power of another 3, we are just counting out the number of factors. And so that just tells me I have 12 factors of 1.1 3 times, right? So in total, I have 36 total factors of 1.01 that I'm multiplying over and over again, right? And so instead of doing it as 2 steps, you can multiply 12 times 3. That will give me 36. So there are 2 different representations. And so 1.01 to the power of 12 to the power of 3 is the same thing as 1.01 to the power of 12 times 3, which is 36. And so those both represent the same account, same account balance because they're just different ways of representing it. We're either saying 36 months or 12 months 3 times, 3 years. So 2 ways of representing, either 36 months total, right, which is 3 years. Each year is 12 months. Or we're saying 12 months 3 times, right? Those are 2 different ways of representing how many months are in 3 years. And so do you agree the account balance is about 1,000, which Kieran says the account balance is about 1,000 times 1.126 to the power of 3. Do you agree? Why or why not? And I want you to look at what we talked about last lesson too. So if I evaluate 1.01 to the power of 12, that is my yearly interest, right? We talked about the idea of a monthly interest. Now we're going to talk about what it means to have a yearly interest, and that's my yearly interest instead of my monthly interest. So remember, be careful with our units of time here. And so in our next activity, we're talking about population projections. And so from 1790 to 1860, the United States population in thousands is modeled by the equation P equals 4,000 times 1.031 to the power of T, where T is the number of years since 1790. And so the first part is stuff that you've been doing for the past lesson, actually past few lessons in Unit 5, right? How many people are living in the U.S. in 1790? What about in 1860? What's the approximate annual percent increase predicted by the model, which they give to you? What does the model predict about the population in 2017, and is it accurate? You can always look that up as well. What we're going to go over together, I want you to answer number 1, but we're going to go over number 2 together. So my annual percent rate is around 3.1% because 1.031 is the same as 1 plus my interest rate, which is 0.031, which is around 3%. And so how do I find out every decade? 1 decade is 10 years. And so 1.031 to the power of 10 for 10 years is 1.36. And we know that my percent increase each decade is about 36% because 1.36 is equal to 1 plus 0.36. So we increase it around 36% every decade. And so this is where we have to be careful about how we are manipulating our time here. We are not multiplying 3.1 times 10 years. No, that does not work like that. Remember, we're taking 1.031 to the power of 10, which gives us 1.36, and my percent value is 36%. And so what would my equation look like? P of D, right? My input is decades now. My output is population. My initial value is 4,000 times 1.031 to the power of 10, which is my annual percentage rate to the power of 10, which is my number of decades, years in a decade, to the power of D. And if you want to represent that using our new percent increase each decade, you can use that value as well. So both those equations represent my number, the population of the United States in terms of by decade, sorry, 8% increase each decade. And so I want you to do the same thing for number 5 in this activity. Sorry, number 3 in this activity. So in many situations, interest is calculated more frequently than 1 year. For example, if you have a credit card statement or if you are buying a loan of any type for a house or a mortgage, usually it's a monthly interest rate. And so you have to keep in mind different compounded interest. And so how often interest is compounded and calculated or added to the previous amount affects the overall amount of interest earned or owed over time. Suppose a bank account has a balance of $1,000 and a nominal annual interest rate of 6% per year. No annual deposits or withdrawals are made. If a bank account compounds interest annually, the account will have one interest calculation in 1 year at a 6% rate. But that doesn't happen every time. And so let's take a look at what our table is telling us. If I'm compounding annually, that means I'm compounding 1 year, once a year, right? Once a year, a whole year goes around, and I compound the entire interest rate of 6%. And so my account balance would be that 1,000 times 1 plus 0.6% to the power of 1, because we're only dealing with 1 year right now. What happens if I'm compounding semi-annually? Semi-annually means every 6 months. That means I'm compounding 2 times per year, right? First 6 months pass, and then another 6 months pass. And so my nominal interest rate is not a full 6% because I'm not doing that every time. I'm compounding 3% because I'm doing 3% the first half of the year and then another 3% the second half of the year, which gives me a total of 6%, but I'm not doing 6% every time. And so how do I represent that? I represent that using compounded interest. And so I still have that 1,000 for my initial rate. I'm still increasing, so I have the 1 plus. I have my 6%, but that 6% is divided by 2 for either the first half of the year or the second half of the year. And I have to do that twice. So I have to take it to the power of 2, right? I'm dividing the interest by 2 because I have to do it 2 times in the year. And I have to take it to the power of 2 because I'm doing it twice in 1 year. And so let me show you two more examples, both quarterly and monthly. And so quarterly is every 3 months. That means I would be doing it 4 times in the year, right? First 3 months, January, February, March, May, April, June, July, March, April, May, June, right? And into August. I mix that up because I'm not saying it off the top of my head. But right, you're doing it every 3 months. If you want to write it out, that'll be easier for you, right? And so you are doing it 4 times. 4 times, and that means I'm taking that 6% and I'm dividing it by 4, which means I have a 1%, 1.5% every time. And so what you're essentially doing is you're taking that $1,000, you're multiplying it by 1 plus that 6% divided by your 4 times of doing it, which is really 1.5. I'm just writing it out like this, to the power of 4, because you're doing it 4 times in 1 year, right? 4 times in that 1 year. If I do something monthly, that I have 12 months in my year, so I have to do it 12 times. I take that 6 and divide it by 12, which gives me 0.5%. And so what I'm essentially doing is 1,000 times 1 plus 0.06 divided by 12 to the power of 12. Because I'm doing it, I have to take that 6%, because I'm doing it 6% for the whole year, dividing it by the 12 times I'm doing it to the power of 12. And so we'll be playing around with compound interest throughout this lesson. So if you, as long this is really your key in terms of how different compounding intervals that we're going to be dealing with. There's no other compounding intervals that we will be working in besides these four. And so I want you to evaluate each of the expressions here. You can use Desmos to assist you. And I want you to figure out, as the more frequently interest is calculated, the balance is greater or less than if I just did it annually. Right? Is it getting bigger and bigger? Is my number getting bigger and bigger, or is it getting smaller and smaller? So I want you to tell me that at the end as well. Here are four expressions and three descriptions. In each case, $1,000 has been put into an interest-bearing bank account. No withdrawals or deposits aside from earned interest is made for the 6 years. I want you to sort the expressions by the same amount of interest into groups. One group contains more than two expressions, and I want you to do that and match it up as well. All of the descriptions have a match. I apologize, I forgot to edit it on this slide, but every expression has a match. Use the directions that you have in your sheet. Remember, we're talking about 6 years here. We're not just talking about 1 year, so be very, very careful about your unit of time. And for number 2, write an expression if the interest is compounded quarterly. We will be talking and reviewing all of that together if you need any assistance, but use the previous slide to help you out with that. And so your learning targets for today, I can solve problems using exponential expressions written in different ways. And I can write equivalent expressions to represent situations that involve repeated percent increase or decrease. And so we'll talk about this more in next class, but I look forward to seeing you there.